Well, indeed, I'm very, very lucky. My talk essentially got written by 3 historic events that happened within days of each other in the last 2 months. Seemingly unrelated, but as you will see, actually all having to do with the story I want to tell you today. The first one was actually a funeral, to be more precise, a reburial. On May 22nd, there was a hero's reburial in Frombork, Poland, of the 16th century astronomer who actually changed the world. He did that literally by replacing the Earth with the Sun in the center of the solar system. And then with this simple-looking act, he actually launched a scientific and technological revolution, which many call the Copernican revolution. Now, that was ironically and very befittingly the way we found his grave. As it was the custom at the time, Copernicus was actually simply buried in an unmarked grave, together with 14 others in that cathedral. DNA analysis, one of the hallmarks of the scientific revolution of the last 400 years that he started, was the way we found which set of bones actually belonged to the person who read those astronomical books, which were filled with leftover hair. That was Copernicus' hair. Obviously, not many other people bothered to read these books later on. That match was unambiguous. The DNA matched, and we know that this was indeed Nicholas Copernicus. Now, the connection between biology and DNA and life is very tantalizing when you talk about Copernicus, because even back then, his followers very quickly made the logical step to ask, if the Earth is just a planet, then what about planets around other stars? What about the idea of the plurality of the worlds? About life on other planets? In fact, I'm borrowing here from one of those very popular books at the time. And at the time, people actually answered that question positively, yes. But there was no evidence. And here begin 400 years of frustration, of unfulfilled dreams, the dreams of Galileo, Giordano Bruno, many others, which never led to the answer of those very basic questions which humanity has asked all the time. What is life? What is the origin of life? Are we alone? And that especially happened in the last 10 years, at the end of the 20th century, when the beautiful developments due to molecular biology, understanding the code of life, DNA, all of that seemed to actually put us not closer, but further apart from answering those basic questions. Now the good news. A lot has happened in the last few years, and let's start with the planets. Let's start with the old Copernican questions. Are there Earths around other stars? And as we already heard, there is a way in which we are trying and now able to answer that question. It's a new telescope. Our team, befittingly, I think, named it after one of those dreamers of the Copernican time, Johannes Kepler. And that telescope's sole purpose is to go out, find the planets that orbit other stars in our galaxy, and tell us how often do planets like our own Earth happen to be out there. The telescope is actually built similarly to the well-known to you Hubble Space Telescope, except it does have an additional lens, a wide field lens, as you would call it as a photographer. And if in the next couple of months you walk out in the early evening and look straight up and place your palm like this, you will actually be looking at the field of the sky where this telescope is searching for planets day and night without any interruption for the next 4 years. The way we do that, actually, is with a method which we call the transit method. It's actually mini eclipses that occur when a planet passes in front of its star. Not all of the planets will be fortuitously oriented for us to be able to do that, but if you have 1 million stars, you'll find enough planets. And as you see on this animation, What Kepler is going to detect is just the dimming of the light from the star. We are not going to see the image of the star and the planet as this. All the stars for Kepler are just points of light. But we learn a lot from that. Not only that there is a planet there, but we also learn its size. How much of the light is being dimmed depends on how big the planet is. We learn about its orbit, the period of its orbit, and so on. So, what have we learned? Well, let me try to walk you through what we actually see, and so you understand the news that I'm here to tell you today. What Kepler does is discover a lot of candidates, which we then follow up and find as planets, confirm as planets, and basically it tells us this is the distribution of planets in size. They're small planets, they're bigger planets, they're big planets, okay? So we count many, many such planets, and they have different sizes. We do that in our solar system. In fact, even back during the ancients, the solar system in that sense would look on a diagram like this. There will be the smaller planets, and there will be the big planets. Even back to the time of Epicurus, and then, of course, Copernicus and his followers, up until recently, that was the solar system. 4 Earth-like planets with small radius, smaller than about 2 times the size of the Earth, and that was, of course, Mercury, Venus, Mars, and, of course, the Earth, and then the 2 big giant planets. Then the Copernican revolution brought in telescopes, and, of course, 3 more planets were discovered. Now the total planet number in our solar system was 9. The small planets dominated, and there was a certain harmony to that, which actually Copernicus was very happy to note, and Kepler was one of the big proponents of. So now we have Pluto to join the numbers of small planets. But up until literally 15 years ago, that was all we knew about planets. And that's what the frustration was. The Copernican dream was unfulfilled. Finally, 15 years ago, the technology came to the point where we could discover a planet around another star, and we actually did pretty well. In the next 15 years, almost 500 planets were discovered orbiting other stars with different methods. Unfortunately, as you can see, there was a very different picture. There was, of course, an explanation for it. We only see the big planets, so that's why most of those planets are really in the category of like Jupiter. But you see, we hadn't gone very far. We were still back where Copernicus was. We didn't have any evidence whether planets like the Earth are out there. And we do care about planets like the Earth because by now we understood that life as a chemical system really needs a smaller planet with water and with rocks and with a lot of complex chemistry to originate, to emerge, to survive. And we didn't have the evidence for that. So today I'm here to actually give you a first glimpse of what the new telescope, Kepler, has been able to tell us in the last few weeks. And lo and behold, we are back to the harmony and to the fulfilling the dreams of Copernicus. You can see here the small planets dominate the picture. The planets which are marked like Earth are definitely more than any of the planets that we see. And now, for the first time, we can say that. There is a lot more work we need to do with this. Most of these are candidates. In the next few years, we will confirm them. But the statistical result is loud and clear. And the statistical result is that planets like our own Earth are out there. Our own Milky Way galaxy is rich in these kind of planets. So the question is, what do we do next? Well, first of all, we can study them now, that we know where they are. And we can find those that we would call habitable, meaning that they have similar conditions to the conditions that we experience here on Earth and where a lot of complex chemistry can happen, okay? So we can even put a number to how many of those planets now do we expect our own Milky Way galaxy harbors. And the number, as you might expect, is pretty staggering. It's about 100 million such planets. That's a great news. Why? Because with our own little telescope, just in the next 2 years, we'll be able to identify at least 60 of them. So that's great because then we can go and study them remotely, of course, with all the techniques that we already have tested in the past 5 years. We can find what they're made of, what their atmospheres have, water, carbon dioxide, methane. We know and expect that we'll see that. That's great, but that is not the whole news. That's not why I'm here. Why I'm here is to tell you that the next step is really the exciting part. The one that this step is enabling us to do is coming next. And here comes biology. Biology with its basic question, which still stands unanswered, which is essentially, if there is life on other planets, do we expect it to be like life on Earth? And let me immediately tell you here, when I say life, I don't mean Dolce Vita and good life, human life. I really mean life on Earth, past and present, from microbes to us humans, in its rich molecular diversity, the way we now understand life on Earth as being a set of molecules and chemical reactions, and we call that collectively biochemistry. Life as a chemical process, as a chemical phenomenon. So the question is that chemical phenomenon universal? Or is it something which depends on the planet? Is it like gravity, which is the same everywhere in the universe? Or we would be all kind of different biochemistries wherever we find them? We need to know what we are looking for when we try to do that. And that's a very basic question which we don't know the answer to, but which we can try, and we are trying to answer in the lab. We don't need to go to space to answer that question. And so that's what we are trying to do. And that's what many people now are trying to do, and a lot of the good news comes from that part of the bridge that we are trying to build as well. So this is one example that I want to show you here. When we think of what is necessary for the phenomenon that we call life, we think of compartmentalization, keeping the molecules which are important for life in a membrane, isolated from the rest of the environment, but yet in an environment in which they actually could originate together. And in one of our labs, Jack Shostak's labs, it was a series of experiments in the last 4 years that showed that in environments which are very common on planets, on certain type of planets, like the Earth, where you have some liquid water and some clays, you actually end up with naturally available molecules which spontaneously form bubbles. But those bubbles have membranes very similar to what the membrane of every cell, of every living form on Earth looks like these. And they really help molecules like nucleic acids, like RNA and DNA, stay inside, develop, change, divide, and do some of the processes that we call life. Now, this is just an example to tell you the pathway in which we are trying to answer that bigger question about the universality of the phenomenon. And in a sense, you can think of that work that people are starting to do now around the world as building a bridge from two sides of the river. On one hand, on the left bank of the river are the people like me who study those planets and try to define the environments. We don't want to go blind because there is too many possibilities and there is not too much lab and there is not enough human time to actually do all the experiments. So that's what we are building from the left side of the river. From the right bank of the river are the experiments in the lab that I just showed you, where we actually try that, and it feeds back and forth, and we hope to meet in the middle one day. So why should you care about that? Why am I trying to sell you a half-built bridge? Am I that charming? Well, there are many reasons, and you heard some of them in the short talk today. This understanding of chemistry actually can help us with our daily lives. But there is something more profound here, something deeper. And that deeper underlying point is that science is in the process of redefining life as we know it. And that is going to change our worldview in a profound way. Not in a dissimilar way as 400 years ago, Copernicus Act did, by changing the way we view space and time. Now it's about something else, but it's equally profound. And at the time, what happened is it related this kind of sense of insignificance to humankind, to the Earth, in a bigger space. And the more we learned, the more that was reinforced. You've all learned that in school, how small the Earth is compared to the immense universe. And the more bigger the telescope, the bigger that universe becomes. And look at this image of the tiny blue dot. This pixel is the Earth. It is the Earth as we know it. It is seen from, in this case, from outside the orbit of Saturn. But it's really tiny. We know that. Let's think of life as that entire planet, because in a sense it is. The biosphere is the size of the Earth. Life on Earth is the size of the Earth. And let's compare it to the rest of the world in spatial terms. What if that Copernican insignificance was actually all wrong? Would that make us more responsible for what is happening today? Let's actually try that. So in space, the Earth is very small. Can you imagine how small it is? Well, let me try. Okay, let's say this is the size of the observable universe, with all the galaxies, with all the stars, okay, from here to here. Do you know what the size of life in this necktie will be? It will be the size of a single small atom. It is unimaginably small. We can't imagine it. I mean, look, you can see the necktie, but you can't even imagine seeing the size of a little small atom. But that's not the whole story, you see. The universe and life are both in space and time. If that was the age of the universe, then this is the age of life on Earth. Think about those oldest living things on Earth, but in a cosmic proportion. This is not insignificant. This is very significant. So life might be insignificant in size, but it is not insignificant in time. Life and the universe compare to each other like a child and a parent and offspring. So what does this tell us? This tells us that that insignificance paradigm that we somehow got to learn from the Copernican principle, it's all wrong. There is an immense, powerful potential in life in this universe, especially now that we know that places like the Earth are common. And that potential, that powerful potential, is also our potential, of you and me. And if we are to be stewards of our planet Earth and of its biosphere, we'd better understand the cosmic significance and do something about it. And the good news is we can actually indeed do it. And let's do it. Let's start this new revolution at the tail end of the old one, with synthetic biology being the way to transform both our environment and our future. And let's hope that we can build this bridge together and meet in the middle. Thank you very much.